Hi, my name is Walker Reed, and this is my lab report for Physics Lab 3. So, for an introduction, the purpose of this lab was to find the mass of the black hole and then use that to determine what the initial velocity of our spaceship must be to avoid hitting either the black hole or the planet that was rotating around the black hole. So some of the fundamental principles that we're using in this lab is Newton's universal law of gravitation, Newton's second law, or the momentum principle, and then the velocity and position update formulas. For a quick summary of results, our mass was found to be 1.9 e to the 34. Initial velocity needed was negative 4.45 e to the 7 and 2 e to the 6, but we'll get more to that later. So some of the formulas used, as stated in the last slide, here are the actual formulas. So gravitation, m times g over r squared times negative r hat, and then the momentum principle, where F net is dp over dt, and it's also perpendicular plus parallel, and then the velocity update and position update formula as shown. So here's part one of the code. Here we set the mass of the star, and then we also set the time period, which was over 1 day, so that's why it is 86,400, because that's how many seconds were in 1 day that the spaceship would be flying for. So on the next part of part one is where I added the formula to find the net force, along with its individual perpendicular and parallel net forces as shown at the bottom. This code, when run, gave me the output of 2 e to the 34 for the mass of the black hole. So now that we have that, then I moved into part two. So in part two, I've started by putting down the mass that I had just found in the last part, and then after that I had to tweak the initial speed to see how it would change the simulation depending on direction, magnitude, and other things, just to see how it would work, and then I'd get down to my exact number later. And then this is the rest of my part two code, and it has all the formulas inputted. So at the top I found r, or the vector that points from the black hole to the planet, and then after that you find r hat by just taking the magnitude. And then once I had r hat, then I could use the F gravity formula, being g times the two masses over r squared times the r hat value that I just found, and then at the bottom I use the velocity and position update formula to update where the spaceship is and how fast it's going. And then after I ran the code in part two, this shows the trajectory. So the magenta line is my spaceship, and the cyan line is the planet, and the black dot in the center is the black hole. As you see, the ship does go very close, but it never actually does hit it because of the breaks in the code. If the ship would have hit, then it wouldn't have shown anything. It would have just said that I crashed into the black hole. So it goes very close, and then it wraps around and keeps moving in the negative y direction, away from the black hole and away from the planet, so out of their orbits and gravitational pulls. So what does this mean? The main difference between the parallel and perpendicular components of the F net and change in momentum is with the perpendicular component. The parallel components of change in momentum and net force have a very similar formula, just the dp over dt, but they just differ ever so slightly. The perpendicular component, however, on net force is just the total net force minus parallel net force, whereas there isn't really a perpendicular change in momentum formula. So in conclusion, there could have been a few potential issues. Number one, finding the initial speed that the spaceship starts at was kind of a guessing game. It took a bit to get the perfect initial velocity, to get where the other formulas would work out and the spaceship would not hit the black hole or planet. And then we're also assuming that the black hole is completely stationary, which could change up some of the values that I found if it were affected by some of the gravity of the planet or the rocket.